For lesson 31.1, the sum of the measures of the interior angles of the polygon, you're going to develop a formula for the sum of the measures of the interior angles, and you're going to determine the sum of the measures of the interior angles. So we know a polygon is a closed geometric figure with sides formed by three or more coplanar segments that intersect exactly two other segments, one at each endpoint. The angles formed inside the polygon are interior angles. Although it is difficult to measure the lengths and angles exactly, tools such as rulers and protractors allow you to measure with reasonable accuracy. So you're going to use the shapes on the next 2 pages and a protractor to measure as precisely as you can. And so you're going to choose any of the triangles or just one of the triangles and measure the 3 angles and record them right here. Then you're going to do the same with the quadrilaterals as well as the pentagons. So as you can see on the next couple of pages, there are different shapes. So you can choose whichever one you would like. There's 2 of each. So pause the video, measure them, and record them in here, and then come back to the video. So now that you have measured the polygons, you should have noticed that the sum of your triangle should be 180 or close, because there is a measure of error because of it being in your book and on an angle and all of that. And then 360, and then for the quadrilateral it should be close to 360. And then for the pentagon, it should be close to 540. So a conjecture about the sum of the measure of the interior angles for the triangle, the conjecture would be the sum of the interior angles of a triangle equal 180. Quadrilateral, the sum of the interior angles of a quadrilateral equal 360. And then a pentagon, the sum of all pentagon interior angles equals 540. So take a minute, pause the video, make sure you write down those conjectures, and then come back. So now we're going to take a look at why the interior angles equal what they do of different polygons, and come up with a formula to be able to find it pretty quick. So if we know the sum of the measure of the interior angles of a triangle is constant, and that the sum of the measures of non-overlapping angles around a single point is always 360, you can determine the sum of the measures of any polygon without measuring. So on number 4, if you use auxiliary segments to determine a way to predict and verify the exact sum of the angles of any quadrilateral and a pentagon, describe your method so that any other group would be able to replicate your results for the pentagon. So you can see here I've drawn a pentagon, and I have created the auxiliary segments from the top point. So it says they can't overlap, so that's why I drew in one here and here. Now if I change the color and go from a different, you can see I could form one here and one here, but we don't want any overlapping. So as you can see on here, we have created 3 triangles. And since we know that the sum of a triangle is 180, if we take 180 times 3, that gives us the 540 for the pentagon. And then for the next one, a hexagon, you can see here that I have drawn in a hexagon. And again, we're drawing in auxiliary lines that do not intersect. And so I've drawn in 3. And so you can see we have 1, 2, 3, 4 triangles this time. And so if I take 180 times 4, times 4, that tells us that the sum of the interior angles of a hexagon would be 720. And you can see here a rectangle. If I draw one auxiliary line, there's 2 triangles, and so that's where 180 plus 180 would be 360, so the interior angles of a rectangle or any quadrilateral would be 360. So to determine the sum of the measures of the interior angles of any polygon, you take the number of sides of the polygon and subtract 2 from it, and then multiply by 180. Because what you have done is you have created triangles, and the number of triangles inside a polygon is always going to be 2 less than the number of sides that it has. So again, if you had a 7-sided figure, which is a heptagon, you would do 7 minus 2 times 180, and then that would give you 5 triangles, which is 900 degrees. So next you're going to take that calculation, or that formula of the number of sides in minus 2 times 180 to find the sum of the interior angles for this chart. So I'm not going to show you the chart just yet. I want you to go through and calculate it, and then pause the video, and go through and fill it out. Then come back and check your answers with the chart. All right, so now that you have had time to calculate, you can see that the measure of the interior angles of each of these different sided polygons. And then if you don't know what polygon it is, it's an n-gon, so it could be any side. You would say the number of sides that it has, minus 2 times 180, or you can say that that's the same as multiplying it times 180 and then subtracting it from 360. That's the distributive property. But because of those auxiliary lines, if we took those triangles out and put them into a circle, it equals 360. So what we're doing is really subtracting 360 from the sum of the side times 180. So again, the number of sides times 180 minus 360 will also give you the interior angles as well. So either formula works. All right, so now looking back at the chart from in question 6, the sum of an angle measures also increases by a constant amount. So that constant amount means that it's linear because it's a constant rate of change. And so you can see that it is increasing by 180. Sorry, my dog is trying to get into the room, and that's the noise behind you, or behind me. So sorry if it's distracting. So again, it's a constant rate. It's a linear because it is a constant rate of change, and it's changing each time a side is added. We're increasing it by 180. And so go ahead and pause the video and take a moment to create the table to plot your data from the table from before. And it says, excuse me, you can or you can see how I made the number of sides and then the sum of the measures of the angles in the degrees. So this side would be the degrees, and this would be the number of sides that the polygon has. So as you can see then, this table forms, it's linear because it is going up by 180 every time. And I plotted the last one wrong, I just noticed, because it was not linear. So it would go up here. And so, excuse me, I have my chart wrong. There we go. That's better. So now you can see the linear relationship. All right, so the data points you graphed above should appear collinear. Write an equation of the line determined by the points. Well, we can see that we're increasing by 180, and we're subtracting 2 from each side. So again, that equation, n minus 2 equals 180. Other ways to write it would be 180 plus n minus 3 times 180, or 180 times n minus 360. So state the numerical value of the slope of the line in item 9 and describe what the slope value tells us about the relationship between the number of sides and the sum of the measures. Well, the numerical value of the slope is 180 because it's increasing 180 every time we're adding a side. And the slope tells us, again, like I just said, each time the side is added to a polygon, and the sum of the interior angles is increasing by 180. If the function s represents the sum of the measures of the interior angles as a function of the number of sides, write a rule for s of n. So this is just function notation. So again, s of n equals 180 n minus 360, or you could use any of these other forms of that. So compare how the algebraic rule is similar to the slope-intercept form. Well, the slope, if it's in slope-intercept form here, which it is, because these two, you would have to convert them to slope-intercept by multiplying and combining like terms, which then it's going to end up equaling this. So the starting value is negative 360, and the slope is increasing 180 degrees. So what that means is if you take the original number of sides times 180 and subtract 360, it's going to equal the total interior angles of that polygon. So here it wants you to determine the value of 7.5. So pause the value and plug this in and then come back and check your work. But as you can see, the answer is there. So you're going to replace the n with 7.5, and so if you take 180 times 7.5 and then subtract 360, it shows you that it would be 990. And if you go back to that chart, that's where this would be right here. So this blue dot right here, 990, would be where 7.5. So here's 6, 7.5. And that would be 990, but it still falls on that linear relationship on that line. And so the domain of S of n would be all whole numbers for n greater than or equal to 3, because the domain is the x, and so we can look at the number of sides in any capacity that are whole numbers. And how can you tell by looking at the graph in item 8 that the function is linear? Well, it's a straight line. The domain is restricted at 3 because you must have at least 3 sides for it to form a polygon. Because that's the definition of a polygon, is in many-sided figure, but it has to be more than 3. So a triangle would be your smallest polygon that would form a closed figure. We couldn't have a polygon that's just 2 lines because it would be open. They would not connect. So that triangle is the 3. So that's where the domain is restricted at 3, is because we have to have a closed shape figure for it to be a polygon. So to recap, you are going to subtract the number of sides by 2 and multiply it by 180, or take the number of sides times 180 and subtract it from 360. So again, you're going to use those formulas to be able to help you find the sum of the interior angles of a polygon. And then your homework, as you'll see, is page 452, and you're going to do these 16 through 22. So go back and pause the video anytime you need to. Go back and rewatch it. Let me know if you have any questions.